All right, so here we are, the concluding chapter of our three-part um, bivariate data trilogy. We're going to continue our discussion of scatterplot and correlation and simple linear regression. We're going to finally talk about one last idea, which is this thing called the coefficient of determination. And we're gonna highlight a new example as we discuss this idea. So here's our example. Help us reinforce some of the previous stuff that we've talked about. Help us kind of stretch out and limber up before we dive into new materials, so we don't so we don't stretch or hurt anything. Now, imagine that we're interested in looking at the relationship between the amount of miles driven on a tire and the groove depth on that tire, right? These tires on our cars, if we look at them, they have these little canyons, these little grooves that kind of slowly wear away as we drive on that tire, right? You hear that expression sometimes when they're completely worn away, that is, the grooves are completely gone. We might say that's like a bald tire. So in this case, our data is in maybe some unusual units. Our mileage is in units of thousands of miles. So an x of 1 indicates 1,000 miles. An x of 10 equals 10,000 miles. Perhaps even a little bit more eccentric is the units for our groove depth. That's in a 0.001 inches. I have no idea what that is. Is it a milli-inch? Is it a centi-inch? I don't really know my metric very well. But here we are. What would that be? Tens, hundreds, and thousands of inches. And so we go out. We take a sample. We sample a bunch of tires. For each of these tires, we measure the groove depth. We make a scatter plot. We calculate the correlation. We find the correlation is negative 0.976. Negative 0.976. Wow, what a strong correlation, right? By far the strongest correlation that we've seen yet. Now, in terms of interpreting this correlation, well, let's go ahead and figuratively speaking, turn the page.
There's a strong, right? I maybe should have said very strong, negative linear relationship between x, the miles that you drive on that tire, and y, the groove depth of that tire. Now, if someone really wanted to try to stump me, they might say, well, what do you mean by negative linear relationship? And I would say, in response to that, I would say, well, the more miles that I drive, the kind of smaller that groove depth is. That's an intuitive idea, isn't it? I mean, that's the whole idea of the groove depth, that the more you drive on it, the more it sort of wears away, right? We call that like a bald tire or a flat tire when it's sort of worn away completely. Say that we go ahead and we calculate, using the formulas in our textbook, we calculate the slope of this line, and we find that it's negative 7.281. We also find the intercept is 360.64. There's a few questions I could ask us, and we'll take a look at each of these in the kind of following slides. I might ask, what's the regression equation? I might ask you to interpret the slope. I might say, how could we know that that slope was going to be negative? And I might ask us to interpret the intercept. Real quick, how do we know the slope was going to be negative? Well, the correlation was negative. And remember, slope and correlation always have the same sign. Now let's go ahead and look a little deeper to find the answers to some of these other questions. So the least squares regression equation looks like y hat is equal to 360.64 minus 7.281x. That's easy enough. How do we interpret the slope? The slope was negative 7.281. What that says is when our miles driven goes up by 1,000 miles, right? This is, remember, a 1 unit increase in x. The units of x are thousands of miles. So a 1 unit increase in x is 1,000 miles. We expect the groove depth to decrease by 7.281, 0.001 inches. Right? So again, it's a little more informative than the correlation insofar as it doesn't tell us just, well, the more we drive, the less we expect the groove depth to be. It quantifies it. It says, well, for every 1,000 miles, this is exactly how much I expect to see the groove depth go down. Now, does it always go down by that exactly? No. Sometimes it goes down by more than that. Sometimes it goes down by less than that. But we would say, on average, we expect it to go down by that much. If a tire has driven, this is interpreting the intercept, if a tire has driven 0 miles, then we expect its groove depth to be the intercept. The intercept was 360.64. Another way of thinking about that is, well, the intercept in this example could be interpreted as sort of the groove depth for a fresh, brand new tire. Right? New tire hasn't had any miles on it. What would we predict the groove depth to be for a car with 15,000 miles? Remember, our units are thousands of miles. So I'm going to plug 15 in there. Y hat is 360.64 minus 7.281. I plug in the 15, and I get that Y hat is equal to 250.425. Easy as that. Now, let's take this example, and let's extend it a little bit, and see how we can use it to kind of teach us about this pretty cool thing called the coefficient of determination. So the coefficient of determination, we give it the symbol r squared, and that's a real appropriate symbol because it literally is that correlation squared. And it turns out that we can interpret this thing as the percent of the variability in y that can be explained by its straight line relationship with x. Sometimes it's just abbreviated as the percent of variability in y explained by x. Note that unlike the correlation, r squared is always non-negative, because you square something negative, it becomes positive. Since it represents a percentage, it makes sense that, and we can show, that r squared will always take values between 0 and 1, just like a percent would. In our earlier example, r was negative 0.976. So the coefficient of determination is you just take that number and you square it. Do that in your calculator, you'll get 0.953. How would we interpret that? We would say, well, approximately 95% of the variation in groove depth in a tire is explained by its linear relationship with its mileage. What might the other 5% be explained by? Well, let's take a step back first and let's think about this, right? What is all this talking about? Well, if you go down to a Walmart parking lot and you start crawling around on your hands and knees with a magnifying glass and a tiny little ruler, and you start measuring the groove depths of all the different tires in the parking lot, you'll come up with an astounding observation. That all these different tires have different groove depths, right? That's what we mean by the variability in y, or the variability in groove depth. Not every tire has the exact same groove depth. There's differences. Now, a natural question becomes, well, why is that the case? Why is it that these tires have different groove depths? And it turns out that one huge piece of this variability is the fact that these tires have driven different miles. One of them's really worn down, one of them looks really brand new. Why is that? Well, one of them's probably driven a lot, the other probably hasn't. It turns out that this explains 95% of the variability, almost all of it. All is a little bit left over. What do we mean by that there's something left over? Well, it means if you and you get a tire, I get a tire, we sort of part ways, we drive around for 15,000 miles, we get back together and we compare our tires. I bet the groove depth will be pretty close, but I'd be surprised if we had the exact same groove depth. That is, there's still differences there, which means that the miles driven doesn't explain all of the variability. What are some other things? Well, maybe driving style, how fast we drive on average, types of roads that we drive on, right? These lurking variables, essentially, explain the other 5%. One last example. Let's say that we do a study. We look at the correlation between x, the time you spend studying, y, the score that a student gets on a 121 exam. We find this correlation to be 0.70. That's cool. It's a positive relationship. The more I study, the better my score. That's encouraging because it makes me feel empowered that I can do something about my 121 exam score. What's the coefficient of determination? What's r squared? Well, it's literally the correlation squared. It's 0.7 squared. how do we interpret that answer, and what else could explain the remaining variability, and why? Actually, these answers are on the next slide, I think. Yeah, here it is. So our r squared, 0.7 squared, plug that in your calculator, you get 0.49. That basically says that we interpret this by saying that 49% of the variability in test scores is explained by the time spent studying. What does that mean? It means that in a little bit you're going to show up, recitation hall, mail somewhere, and you're all going to take an exam. And you're probably all going to get different scores. If you all turn in your exam and you all got the same score, I'd be very surprised. I'd accuse everyone of cheating, right? It would be so striking if that were to happen. Why is that? Why do different students get different scores in the exam? Well, one answer to the question is, well, different students have spent a different amount of time studying. And it turns out that that explains very close to half of the variability, which is a lot. It's a big piece. Probably the biggest piece out of anything. But it's not the whole picture. That is, if two of you made a pact, hey, we're both going to study 10 hours, nothing less, nothing more, probably odds are you're still going to get different scores. It'll bring your scores probably closer together than if you had studied a different amount of time. But again, it doesn't explain all of the variability. I'd be surprised if you all had the same score. Why do you still have different scores? Well, you might have spent different times sleeping. You might both have different levels of motivation. You might both have had a different sort of quality of the time spent studying. Maybe one of you is in the library, it's quiet, you're really focused. The other one was kind of watching a movie while you were doing it. And maybe you just have different math backgrounds, right? I'm sure you could think of other variables if you kept going. These other variables are sort of the remaining half, that remaining 51%. And I think this does it. So good luck with your studying. As always, if you have any questions, don't hesitate to send me an email.